in question 5, we have alpha being, or A being 1, 2, 3, 4, and we're having projection onto A. We let alpha and beta be the standard basis respectively for R4 and R. Now we want to compute what P alpha of A, or P of A alpha to beta. So what we're looking at here is we're looking at what is P A applied to 1, 0, 0, 0? What is P A when we apply it to 0, 1, 0, 0? PA applied to 0, 0, 1, 0, and PA applied to 0, 0, 0, 1. Now, when I look at this here, this is going to equal the inner product of 1, 0, 0, 0 with the inner product of 1, 2, 3, 4, all over the inner product of 1, 2, 3, 4 with 1, 2, 3, 4 times the vector 1, 2, 3, 4. Okay. This should be 4 here. They should be R4 and R4 respectively, because we're projecting onto a 4-dimensional space. So here, what I'm going to do to save computation time later is this piece here is going to be in all of my computations. So I'm just going to solve for what that is. 1 squared plus 2 squared plus 3 squared is 4 squared, because it's the first times the first plus the second times the second plus the third times the third is 1 plus 4 plus 9 plus 16. 5 plus 25 equals 30. Okay, so that's going to be 30. So this is going to equal 1/30 of 1, 2, 3, 4, which equals 1 over 30, 1 over 15, 1 over 10, and 2 over 15. So this here is going to equal 1 over 30 E1 plus 1 over 15 E2 plus 1 over 10 E3 plus 1, 2 over 15 E4. In my second example, we project this vector. This is going to be 2 over 30. 1, 2, 3, 4, or 1 over 15 times 1, 2, 3, 4. This here is going to be 3 over 30 times 1, 2, 3, 4, or 1 over 10 times 1, 2, 3, 4. And this here is going to be 4 over 30 times 1, 2, 3, 4, which equals 2 over 15 times 1, 2, 3, 4. And this is going to give us a really interesting matrix with lots of fractions. So we get 1 over 30, 1 over 15, 1 over 10, 5 over 15, or 2 over 15. Then our next example, here we're going to have 1 over 15, 2 over 15, 1 over 5, and 4 over 15. Okay, and then we're going to have 1 over 10, 1 over 5, 3 over 10, 2 over 5, and finally we're going to have 2 over 15, 4 over 15, 2 over 5, 8 over 15. And that's our matrix representation. So this is P A of alpha beta, given they're both R4. Okay. Now, one thing we can do to kind of make things a little bit easier is we're going to rewrite this as the vector, the matrix. We're going to factor out a 30. So we're going to do 1 over 30 times, this becomes 1. This becomes 2, 3, 4, 2, 4, 6, 8, 3, 6, 9, 12, and 4, 8, 12, 16. The matrix becomes a lot nicer if we factor out that term 1 over 30. Now, without matrix multiplication, we're going to compute what this is. So what we're going to do is we're going to compute what PA 1, 2, minus 3, minus 4 is using the basis beta. Now, in order to do that, first what I'm going to do is I'm going to figure out what this is just using the definition. So this is the inner product of 1, 2, minus 3, minus 4 with 1, 2, 3, 4 divided by the inner product of 1, 2, 3, 4 with itself times the vector 1, 2, 3, 4. Here, we know what the bottom of it is. We know that it's 30, but the top is going to be 1 squared plus 2 squared minus 3 squared minus 4 squared all over 30 times the vector 1, 2, 3, 4, which equals 5 minus 9 minus 16 over 30. Minus 4 minus 16 is minus 20 over 30, or minus 2 over 3. And again, this is just scratch work, so this becomes minus 2 over 3 times the vector 1, 2, 3, 4. So it equals minus 2 thirds minus 4 thirds minus 2 minus 8 thirds, or P A of 1, 2, minus 3, minus 4 beta is going to equal, we take the first coefficient, this here, or sorry, before we go to here, we got to represent this using our standard basis. So this equals minus 2 over 3 E1 minus 4 over 3 E2 minus 2 E3 minus 8 over 3 E4. So P A of 1, 2, minus 3, minus 4 equals minus 2 thirds minus 4 thirds minus 2 minus 8 thirds. Okay, now calculating this vector using alpha, well, 1, 2, 3, minus 3, minus 4 equals 1 E1 plus 2 E2 minus 3 E3 minus 4 E4, which implies that 1, 2, minus 3, minus 4 alpha equals 1, 2, minus 3, minus 4. And now we want to show equality. So what we're going to do is we're going to do 1, and here to simplify this, we'll write 1/3 or minus a third, and we're going to get 2, 4, or sorry, minus 2 thirds. I'm going to get 1, 2, minus 3, minus 4. And we're going to show that when we do the matrix multiplication of 1/30 times the matrix 1, 2, 3, 4, 2, 4, 6, 8, 3, 6, 9, 12, 4, 8, 12, 16 times 1, 2, minus 3, minus 4, we get what we're looking to get. Well, this is 1 over 30, 1 plus 4 minus 9 minus 16. And now 2 plus 8 minus 25 minus, or sorry, not 25, minus 18 minus 32 minus 3, or sorry, three plus 12 minus 27 minus 48, and 4 plus 16 minus 36 minus 60 equals 1 over 30 times minus 20 minus 40 minus 60 minus 80, which equals minus 1 over 3, 2, 4, 6, 8, which equals minus 2 over 3, minus 4 over 3, minus 2, minus 8 over 3, which is exactly what we wanted to verify. This question really hinges on the rank-nullity theorem. So in this question, we have a linear transformation, and V and W are both finite dimensional. And we're proving that if T is injective and T is surjective, then dimension of V equals the dimension of W. Well, if T is injective, then the dimension of V is less than or equal to the dimension of W. If T is surjective, then the dimension of V is greater than or equals the dimension of W. As the dimension of V and the dimension of W are both finite, the dimension of V equals the dimension of W. Now, we want to go prove that if the dimension of V equals the dimension of W, then T is surjective if and only if T is injective. Here, what we're going to do is we're going to leverage those following are equivalent. Those two, the following are equivalent statements. Specifically, T is injective if and only if the dimension of the kernel T equals 0, and T is surjective if and only if the dimension of the image of T equals the dimension of W. Okay, and the linchpin here, the key point of the argument, is the rank-nullity theorem. Rank-nullity says that the dimension of the image of T equals the dimension of the kernel of T. Or sorry, the dimension of the image of T plus the dimension of the kernel of T equals the dimension of V. So let's start with surjective. If T is surjective, then the dimension of the image of T equals the dimension of W, which equals the dimension of V. By rank nullity, the dimension of the kernel T equals the dimension of V minus the dimension of the image of T, which equals the dimension of the V minus the dimension of V, which equals 0. Thus, T is injective. Now, the other direction is very similar, and I'm going to leave that as an example. Start with it's injective and go and show that it's surjective.